context of this project is linked to the fact that the title is from wastewater treatment plant to water recovery factory, resource and recovery factory. So it means that before we were used to call the place where we treat wastewater treatment plant. And now we shift to something new and we say, okay, waste is not only waste, it could be resource. Resource of what? Resource of energy with the carbon, resource of nutrients with nitrogen and phosphorus, and resource of water, of course, because in wastewater, 99.8 maybe or 0.7% is water. So our research are dedicated to fit to the Sustainable Development Goals from UN and to complete or to solve some trouble or some problems, issues linked to the water, food, energy nexus. So, the conventional way to treat wastewater are those well-known aerobic processes, activated sludge, conventional activated sludge. So, those figures say that if you want to treat 100 kilograms of chemical oxygen demand, so the organic content, which is the main pollutant that are in the wastewater, we have to spend around 100 kilowatt per hour, and we will produce a big amount of sludge to be disposed, which will cost a lot also. We will lose some heat, and at the end we will produce a water, treated water, an effluent that could be discharged in the environment to fit to the regulation. So we are able to have a really good quality of water. But the trouble is linked to this energy demand, and I found those figures, not so recent, but it's good to have in mind that in the world there is only 20% of the wastewater which are treated. The Sustainable Development Goals from the UN say that we want to treat maximum of those wastewater. So we want to increase the wastewater treatment of those in the world. But at the moment, 1% of the world energy consumption is due to this wastewater. So it represents around 50% of USA energy consumption. So if we want to increase the amount of wastewater which has to be treated, we will also increase the energy demand. And right now we all know that energy demand is a key problem, and we want to decrease this energy demand. So that's why in our lab we shift to the anaerobic processes, which has the good advantages to consume quite no energy, because we don't provide aeration and we don't provide the oxygen, and oxygen aeration is the main source of energy consumption in the wastewater treatment. And we can produce energy in form of methane, because the carbon, the COD, is transformed by the microorganisms that grow in those anaerobic processes into a methane which could be a source of energy and heat. We produce less sludge because those microorganisms are low-rate microorganisms, and what could be a trouble is that we produce an effluent with a lower quality. That's the conventional anaerobic processes, which is called methanization, and because of the low rate of those microorganisms, those processes are conventionally used, or actually, or nowadays is used for industrial wastewater with a high loading rate, and not for the domestic wastewater. So the advantages are the low sludge production, so low cost, low energy consumption, because it doesn't mean that there is no energy consumption, it's lower, really lower than the aerobic processes, and the possibility to produce energy in form of methane. So challenges remains. Challenges due to for the domestic wastewater to apply those processes to the domestic wastewater. One of the challenges is that the domestic wastewater is mainly water, so the organic loading rate of this wastewater is really low. We have to work at ambient temperature because I didn't say that, but anaerobic microorganisms are at the rate of degradation which is proportional to the temperature. So the optimal temperature for those microorganisms is around 35 degrees. That's why those processes also are really well found in some countries where the temperature is high, like in South America, in Brazil, for example. There is also the fact that if we work at lower temperature, we will change the equilibrium between liquid and gas, and we will find more methane that we produce by the bacteria in the liquid phase. So it means that we will discharge an effluent with methane dissolved in the liquid phase, which could be released later in the environment, and so we will produce some greenhouse gas. So that's a trouble too. So what is just after this short introduction and to comparison between aerobic and anaerobic, in the project of Lucy, we decided not only to apply the anaerobic digestion that I showed you before, but also to add some membrane, because I'm working in Institute European Membrane, so I have to put membrane somewhere in my project. No, I believe also in membrane. So the membrane that we add, it's like a filter, like the coffee filter. The goal is to do a physical clarification. We'll see later, but the pore size, it's really low. It's less than around 0.04 micrometer, so it means that no bacteria can pass through. And so it is a physical clarification, and it is also a physical disinfection. So it means that at the end, we produce an effluent without any bacteria. So anaerobic digestion membrane bioreactor, it gives high MBR. And granular sludge, why? Granular sludge, it means that all the microorganisms, which are normally found in a free mode, are flocculated, so they stick together naturally by producing some proteins and everything. Okay. It is found also in the nature that those microorganisms, after growing in kinds of flocks, they could grow until which we call granules. We got pictures of the granules here. It's like a semoule, like I don't know if semoule is the word that I can use. It's something we eat like in the couscous. No couscous? Yeah. Okay. So it's like a small ball of microorganisms. It could be, we say granules when it's up to 100 micrometer of diameter. And we found in our system some granules like to 2-3 millimeter. So 2-3 millimeter, it's becoming big. And this biomass aggregation is natural. It takes time, and what is the mechanism of this formation of the granules is that the microorganisms also grow. They like build a mineral earth made of calcium carbonate. Okay, so it's like their media, and it is stored inside the granule, and then they grow outside. Those granules have got many advantages because there are a big diversity of microorganisms inside. You can find, because the substrate that they see is not the same when it is at the external surface of the granule or inside the granules. So it means that there is a diversity, there is an ecology of the granules which is really rich. Also, it has been used because it has settling properties really interesting, because it goes really fast down to a settler. So at the beginning it was used for that. So settling capacities, microbial diversity, and also in this shape, in this form, the microorganisms are really less sensitive to some shocks. It could be toxic shocks, temperature shocks, feed shocks, every kind of shocks that the microorganisms could have. They are like protected in the granules. If there is a big toxic that happens in the wastewater, maybe the bacteria at the external surface will be affected, but inside there will still life. So that gives us to the granular anaerobic membrane bioreactor. And the goal of my speech today is to show you our first experiments of this kind of system to treat domestic wastewater at the scale of a laboratory. So, it's something I already said in the previous slide, but I will say it again with maybe some figures added, just to be sure that you remember this. So anaerobic digestion, it can save that up to 90% of energy for wastewater treatment. We convert organic matter in CH4, so it is a source of energy. We have less sludge to manage after the treatment, like the figure interesting is like five times less. So it decreases the cost of the global treatment of the wastewater treatment plant. About granular biomass, and we have this something, that's why it's good to have this kind of slides, because I forgot to tell you this also. This is really interesting, because with the granules, we can have microbial or bacterial density concentration into the system really, really higher than the conventional activated sludge, CAS or conventional activated sludge. We can go up to 20, 40 grams per liter of microorganism. And it is really interesting because it could allow to intensify the process, to have in a smaller volume, a bigger quantity of microorganisms, and so a more compact system, which is important when there is some problem of land capacity or land place for the facility of treating water. So strength, compactness, and potentially also decrease membrane fouling, because in membrane fouling studies, we found that which is the more impactant for fouling, because when you apply a membrane, you want to do a filtration for a long period, and after some times there is some cake deposition on the membrane, there is something that deposits, some interactions between the matrix that you want to treat and the membrane. So it conducts to a decrease of the flux, a decrease of the production, and so you have to clean. And we know that which is what is really impactant in the fouling is some kind of sludge yes, so bacteria and their proteins that stick to the membrane. And some results in the literature, let's think that the granules promote less fouling than the flux. So membrane filtration allows to have really high quality of water at the outlet of the wastewater treatment plant because of the total biomass and suspended solid retention. It allows also to have more compact systems. So, what are the challenges? I told you before, in the domestic wastewater, we have low loading rate, so low carbon content because it's really diluted, and we have to work at what we call psychophilic temperature. It means low temperature for those kind of microorganisms. So you could ask me, okay, you talk about low temperature, 25 degrees. It's quite high temperature. I don't know the mean temperature of the wastewater in Louisiana, but it could be a little bit less than 25 degrees. I guess that it could be around 20. In Montpellier, it's around 17. And so if we decrease this temperature, we will have two issues, two big ones. Well, the first one is that we decrease the biomass activities, because biomass activities is linked to the temperature. And the second one is that we increase the CH4 solubilities, which conduct to the loss of methane in the effluent and the So this loss has two consequences, bad consequences. First one is that we lose energy, and second one is that we release a potential greenhouse gas in the environment, and something we don't want. So that's our challenge. Working at this low loading rate and working at this low temperature. And in the literature, you see this figure is quite impressive and quite, which could lead to why do that? Because I said that it's good to use anaerobic treatment to get some energy, but in the literature we found that from 30 to 90% in certain paper, in certain studies, that the CH4 that we have produced is lost into the effluent. So we produce energy, but we cannot get it. So it gives bad balance, and it's not working. So that's our challenges, and I wanted to show that maybe it could work. And the goal is to increase the energy efficiency and to decrease the greenhouse gas emissions potentially. About membrane fouling also, so I explain you quickly that this mechanism appears, and each time we use some membrane, we have to fight against this to find some way to mitigate this membrane fouling. And something we found also is that what we can see in the literature is that like up to 70% of the energy consumed in the wastewater treatment plant based on the membrane bioreactor is due to the gas purging, because of which we use to control the fouling. So gas purging, it means that we inject some bubbles at the bottom of a membrane, and with these bubbles, these hydrodynamic conditions, it allows to avoid the formation of the cake on the membrane, and so it permits to conduct the filtration for a longer period, but we consume a lot of energy. So, another thing is that in the literature we found that around 75% of the experimental setup put the membrane outside the system. Like this, you have the bioreactor with the microorganism, and you put the membrane outside, you do some gas purging. It's the way to prevent the fouling. So this is what we found in the literature, what is conventional, because it's, the fouling is really something that membranologists, the people who are working with membrane, who are really afraid of. So they want to apply some configurations which are really preventing from fouling. So here in our case, what we have done is that we put the membrane inside the granules, and we decided not to do gas purging, because our goal was to reduce the energy consumption. So we say, okay, if I put the membrane inside, I will have a more compact system. If I don't apply gas purging, I will promote fouling, but it will give less energy demand. So that was the goal, to shift to this system, conventional one, to this new system, which on the paper is not the best one. Another thing is what is the hypothesis of using this system was also that with the membrane we can retain all kind of microorganisms. It means the granules, it means the free bacteria, but it means that also we will increase the retention of the dissolved and colloidal organic matter. And this matter, this content, are supposed, for our feeling, that it will increase the biogas production potential of our system. Because of the membrane, we can retain more things, and we can have a system that produces more biogas. That's what we expected, and that we wanted to verify with this study. So one-stage reactor, the membrane inside the granular anaerobic digester to be more compact, distilled wastewater treatment really diluted, and low temperature. About the system, about the setup we used. So here you see some pictures of the granules we take. So we started with granules. It means that we get to a paper mill factory where they use granules to treat high loading rate wastewater. So you see the granules, like it's a spatule from the lab. So those granules are quite big. It's like, I think that this is quite 1 millimeter. So we take those granules to seed our reactor and to start quickly. And in our lab, we have done this setup with 2 reactors in parallel. One, it is called the conventional, UASB, without membrane. And the second one is a granular anaerobic membrane reactor with the membrane. So it means that the outlet of this system is only the supernatant, okay? So the granules are there. There is a recirculation to promote homogenization, and we recover the treated water in the supernatant. And in this system, in the MBR, we recover the treated water through the membrane, which we call the permeate. But we have still the loop of supernatant in order to have a mixed system. There is no styrene in the system, okay? So we have to turn. And we fed those 2 systems with the same feed, which is a synthetic one, close to the real one. And this is the membrane we use, so it's flat sheet membrane. Here we see only 1 face, but actually there is 6 faces, and it is supported by the middle of the membrane. It is submerged into the system, and we recover the permeate by this hole. Okay, so we have bisection pump, which is here. No, sorry, here, this one. So we do suction and we recover the permeate. So it means that the effluent is there with the granules, and it passes through the membrane and goes at the collecting hole inside and go outside. This is the pore size of the membrane. This is membrane from Germany, which is the material is PES. And the operating conditions we apply, so it's 25 degrees, so it's a little bit up to the membrane, the Montpellier temperature of wastewater, mean temperature, but we didn't want to be in a too worse condition for the bacteria, so we decided to go to 25 degrees, and this organic loading rate is a conventional organic loading rate for domestic wastewater. Something also is that this is a flux that passes through the membrane, so it means 1.3 liter per square meter per hour. It's really low flux, so that's also maybe a trouble of our study. But at the start, we wanted just to show the effect of the membrane on the biogas production. So we decided not to be too high in terms of membrane flux, because we could have some more trouble, more disturbance of the system, because if we work at high flux, we will have to clean more often, open the system, check the membrane or everything. So we decided to work at low flux to start, in order just to check what's going on with the membrane. So in terms of analytical methods that we use the classical one for the wastewater treatment plant, for the wastewater treatment system. So organic carbon with COD and total organic carbon. The mixed liquor suspended solid, the volatile suspended solid. We check the intermediate of the anaerobic digestion, which is volatile fatty acid. 3DM is used to have the nature of the organic matter with fluorescence spectroscopy. For the biogas, we have analyzed the biogas in the liquid and in the solid phase, in the liquid and in the gas phase, because I told you there is some methane which is dissolved. And we have also done some characterization of the granules by classic particle size distribution, sludge velocity index, or surface, and this is SMA is also the activity of the granules. It's like methanogen potential activity or something. Okay, so let's go to the results. So here, before the zeros, there were like more than 1 year of acclimatization. It was during the pandemic, during the lockdown, so not so easy to conduct a bioreactor and to feed them, but it allows us to sometimes to go out from home because we had the opportunity, authorization to go to the lab once a week, so just to feed. So it was 1 year of COVID, and then in July we were able to go again in the lab, and we are following during 120 days the system. So what we see here is COD removal rate for the two systems. In blue you have the conventional one without membrane, and in yellow you have the anaerobic membrane reactor. So the first thing that we see is that during the starting period, the membrane provides directly a really good quality effluent. So we have around 90% of COD removal, but in the USB we have a starting period of around 30 days. So it was the first good result that membrane could allow to have a really short starting period, and really quickly we have a system that goes well. Another thing that we see is during the stable period, if we do the mean COD removal of the yellow and the blue, we see that we have up to 10% more of COD removed by the GN MBR with the membrane than the USB. So this was the good point. Okay, you put the membrane and you can increase the removal of organic matter, so you can have a better effluent quality. Which was really interesting, because we can reach the same quality as the aerobic treatment. So that was a good point of this COD removal study. Then we have the results of the biogas production, and you see that in the granular anaerobic membrane bioreactor, we produce more methane than in the USB. In fact, so the unit here is a normal liter of CH4 per day. We produce 0.85 in the GNMBR in comparison to the 0.57. So it's a really upgrade of the system. So why? What's going on? So here is the mass balance of the two systems. And with the mass balance, we can have the explanation of what happens between the two systems. So in the mass balance, we have here the influent, so it's 100%, and then we have the different mechanism of removal of the COD. So there is the effluent, there is CH4 in the gas phase, CH4 in the dissolved phase, so in the liquid, the COD which is used by the sulfate reducing bacteria, and the COD which is used for the growth of the biomass. And what you see here is that, the conversion of COD into CH4 is higher in the GNMBR than in the USB. That's what we found. We produce more biogas. So we see it here. And the total production is the sum of these two. Okay. What we see here is that more COD remains in the GNMBR. It means because in the effluent, you have less COD in the GNMBR than in the USB. So those COD, which is dissolved colloidal organic matter, is retained by the membrane. So this COD, because of the long contact time between this organic matter and the bacteria, is transformed into biogas. So the fact that we have the membrane, we can retain more content, more macromolecules that are later transformed into the biogas. So that's the good point of the membrane. We had verified it by the 3D EM, which is fluorescence spectroscopy. And so what you see here is a map of the organic matter. in the supernatant, so in the content, in the supernatant of the GNMBR, and in the outlet, in the permeate. So this kind of map, for those who are not used to, is so in emission excitation also, and the intensity of fluorescence is those colors. If it's red, it's more intensity. If it's blue, it's low intensity. So it allows to have an idea of the kind of organic matter we have in this system. And so it is divided in different zones that are linked to different nature of organic matter. So here we have the humic and fulvic acid. Here we have the soluble microbial products, and here we have some proteins linked to the biological activity. So what we see here, if we compare the supernatant to the permeate, is that this big intensity of fluorescence disappears when the liquid passes through the membrane. So it means that there are some compounds which are dissolved, because this measurement is done in this dissolved phase. So those dissolved compounds, which are lower than the pore size of the membrane, are retained by the membrane. We see clearly the disparition, the removal of these compounds. So we believe that this is those compounds that are transformed into CH4, and that could explain this higher biogas production when there is a membrane. Additional CH4 due to this dissolved and colloidal organic matter. And if we compare, to the USB, you see in the effluent, in the supernatant, which is what is discharged from the USB, we found this fluorescence in those areas. So it means that in the USB, this organic matter dissolved and colloidal are discharged. So this is why we have lower biogas production when there is no membrane. One last thing related to this mass balance is that in the USB we have more COD, which is used for the biomass growth. So potentially we have more biomass growth and more solids to discharge. And so it is another point to say that GNMBR works more than the USB, So I'm going to my conclusion, to the main figures of this study, is that so in the GNMBR you can upgrade by 30% the biogas production. You can have up to 93% of COD removal, which is more than 15% of the USB without membrane, and you can reach some effluent quality really close to the aerobic one. And we have done also the energetical assessment for this system. I didn't show it in this talk, but you can see it in the publication that I hope that will be published soon, that this system is positive in terms of energy. So instead of consuming 1 kilowatt for 1 kilogram of COD, we can produce around 0.1, 0.15 kilowatt per kilogram of COD. So it means that instead of consuming energy, we produce energy by treating the water and getting really good effluent quality. So just to finish about what we will do later, we will try with Lucy. We try to work at higher flux to intensify the process. We have also some studies related to the membrane fouling to understand really more deeply what's going on, what kind of mechanism leads to this membrane fouling. It's really links to also to the flux. And I've also in my team a postdoc, Kazi, who work on the recovery of this dissolved methane. Because at the end, you see that there is around 15–20% in my study of the methane which is in this dissolved part. So we are using also membrane, hollow fiber membrane contactors with hydrophobic membrane to recover this methane. And The results of this study has already been published, and we can say that we can recover 100% of the methane from the permeate with membrane again. So Lucy wanted me to show that because she took some pictures of the granular sludge, and she is really proud of this dog. But she found the dog here. I don't know if you find it. And so this is a granular dog, something like that. Thank you very much.
Thank you. Questions?
So with the dissolved methane in the effluent, have you considered using like a heat exchanger or something maybe to like lower the temperature, and then more of that goes to the
Heat exchanger in order to warm the
to like lower the temperature of the effluent so that the methane comes out of the
we don't want to do that for the reason that we want that this system would be applied for domestic wastewater treatment. So if we use a heat exchanger, it would be really a great idea, but it means that we will have to warm a high quantity of wastewater, so we will spend energy. So and our goal is to decrease the energy to spend. So that's why the heat exchanger was not at all a solution for us. Because, and if we wanted to heat the effluent, we can also heat the bioreactors, and we will have higher activity also. So yes, we wanted really to try to work at this temperature, because for a domestic wastewater treatment plant, it's not at all a solution to warm. It's too big volume.
Yes, please. Can you talk a little bit about ammonia? I mean, an obvious disadvantage of doing anaerobic stuff is you're going to have high ammonia in your effluent, right?
Exactly. So one of the trouble of anaerobic digestion, anaerobic systems, is that we didn't touch any at all, but we have no possibilities to touch ammonia, nitrogen, and we know that we have to remove it if we want to protect the environment from eutrophisation. There are many ways to answer your question. One is that we wanted to reuse our water, and maybe it could be good to keep the nutrients inside the effluent in order to do irrigation, direct irrigation. So if we keep the ammonia, it's not anymore ammonia, but the nitrogen form. If we get it stable, we can also use our effluent for fertigation. Other kind of possibilities is to add a tertiary treatment like algae growth, or there are also photo granules. There are many ways or many other processes to treat ammonia. It's true that it's disadvantageous if you want to discharge directly our effluent. It's not possible because it will be too high for the nitrogen contents. But yeah, we are trying to, well, there is a way to use directly the effluent or to add a treatment. But for sure, in anaerobic digestion, you won't touch ammonia.
Is the quality of the granular sludge in this anaerobic reactor different? Are there elements like cobalt or nickel that could be recovered that may not be in the aerobic?
The question is about the role of the metals in the.
Is that a resource? Are they there at high enough concentrations over time to make them recoverable, or?
It's something we didn't check, but what I heard is that the microorganism needs some really small quantity of those metals to grow, and because of the shape of the granules, they also have some capacities of absorption or storage of those compounds. It's something we didn't check, but I for sure they need some trace of those microelements to grow. But yes, we didn't check this. But something maybe to go deep.
How do you know if the membrane fails? I'll ask it if you're not going to ask it. So you're working on a project. How do you know if in an MBR the membrane fails? How can you detect a small pinhole or a very minimal failure of the membrane? in the effluent.
Mhm.
She's working on a method.
Okay,
to do
good,
it.
but we can.
And so she's
It's-
not gonna ask a question. I'll
No. There are some way to membrane phase. Okay, I understand. It's flat sheet, so there are less trouble than the hollow fibers that could are more fragile, but it could have still problems. We could detect it in the effluent if we see that there are some suspended matter or suspended solids into the effluent. Could be an option. I would like to say to know on which kind of system is working. You are working related to this membrane phase. But let me know. Well,
tell them what your solution would be.
yeah, what is your solution?
We found that it's turbidity, mainly. We've also looked at, Great.
But what are you using to
Oh, we're
detect
doing
that?
DNA amplification through layup cycle, which is faster than PCR.
To detect the concentration of the peppervirus in the effluent.
And you do it online? Why you want to apply it online?
Yeah.
For drinking water.
Yeah. Well, for wastewater.
For wastewater?
Yeah.
So
Because
there-
pepper virus is a plant virus, but it's the most common virus in wastewater.
So it means that we got MBR in the area?
That's it.
Yeah.
No.
This is a national competition, and this is one of the
Okay.
tasks that they're working on. So there's not many MBR. There's only one applicant.
There is one in Louisiana.
Yeah. I think something like that. Yeah. A lot of Texas, so nearby.
Okay, nice.
It's working. They tell me it is.
So I've got a question. For the amount of biomass that you're producing, it's lower than normal systems, but do you, like, how often do you have to clean it out and remove biomass? And is that removed as the granules, or is there something like, do you size select, or how does that work?
In our system, it is running since 2 years, and we have never discharged any biomass. We are in a lab scale system, but there are many papers that talk about infinite solid retention times. So it means that you never discharge any biomass, which is magic, because at the end there is still some solids. And we also decided to work with the synthetic wastewater, but we added some solid compound, quite some solid matter in this, because we wanted just to verify. And but it's really hard to know exactly the solid content in the system, because when you have a flocculated biomass, you can style it, you can take a sample really quickly and to be sure that it's homogeneous. When with the granules, it's completely impossible to style it, so we think about many ways to measure those biomass. And to be honest, when I go to the COD balance, the solid, because the biomass growth is the results of the COD mass balance. So we were not able to we were disappointed about that, but we were not able to measure those solid contents. It's really hard. We had some ideas about putting the bioreactors onto big balance and to check those biomass growth. But yes, we discharge a little bit of biomass when we do some sampling to analyze for the balance, because I didn't show everything, but we have also done the particularized size distribution or something. We have analyzed the membrane, the granules also for those pictures and everything. So it was the only time we took some samples of the granules, but we never discharged it. And in the systems that are running for industrial scale with granules, they told us also that they discharge really rarely. These big systems, and they don't have to discharge the granules. But once says that, it's true that what we also found when we analyze the characterization of granules a long time is that the granules grows in terms of size, but this is also the mineral contents that is growing. So it says that the granules is becoming more and more inert, more mineral content. So yeah, they could have trouble at the end, because if it's only mineral, it won't be good. And yeah, that's something for the industrial scale and for the longer period, but yes, seems good question.
Any other questions? Well, thank you again. I did get the live stream working, so after
my
a couple
friend,
slides,
maybe.
we got it
Friend.
working.
What time is it?
If you were lured here for participation credit, sign in. And otherwise, please enjoy some refreshments. Take a few minutes to get to know Dr. Lesage. Thank you for coming.
Yeah, thank you very much for coming.
Hi, Dr. Lesage. Yeah, I have a quick question. Experiment.